Mr. Efron here, and here's a short video to help you with the Centripetal Motion Lab, the virtual version. So normally in class we would set up something similar to this, a plastic tube with some rubber stoppers attached to it, and then we'd have a fishing line string go through the tube, and then at the bottom we would connect some brass masses, which we would use to provide the centripetal force. So that provides some tension. And that tension force then provides the centripetal motion for the rubber stoppers. So if I get a chance, I'll shoot a little bit of a video of that, what it looks like in class, and post that as well. So here's the main formula right here. Your centripetal motion is equal to mass times centripetal acceleration. We're going to be using the formula that uses period, 4 pi squared r over t squared. And of course, if you look at the simulation here, we would be using hanging masses, uppercase M, times G to provide the force. Now, if we rearrange this to solve for T, the period, the time it takes for one revolution, we end up getting this formula right here. T equals 2 pi root M root R over root of the force, mg. And then if you want to make it look like a y equals mx plus b, or a linear function, then we can say that we're going to have a slope of 2 pi and a y-intercept of 0. So now we can't do this live because we lack the equipment, so we'll be doing the virtual version, which looks like this at the physics classroom. So I'm just going to open this hyperlink. Right here. And actually here, let me just grab that and pop it into a new window. Just give me a second here. Here it goes. So in this simulation, there's a few things you want to do. The first thing you want to do is show the forces on the object with components. So that'll help you with the some of the questions later. The force labels. There we go. And then you want to show the values right here so you can get the values when you need them. Then what you're going to do is set it up as shown in the lab sheet. In the lab sheet here, we're going to set the viewing angle to 10 degrees, the radius to 0.25 meters, and we're going to set the mass to 3 kilograms and the speed to 2 meters per second. When you change the speed, that will change the force. So you just go back to the simulation and you do the following. So that's 10 degrees, that's 0.25, and change the mass to 3 kilograms. There we go. And we're going to change the speed to 2 meters per second. Then you should be able to read any values you need. So for example, the centripetal motion right here, it's kind of hard to see on this web page. Let's see if I can scroll in a bit. It's 48 newtons. If you need the tension, it's 56.6 newtons. And okay, you're not supposed to look up the period, but it's 0.785 seconds. Then what you want to do is get a stopwatch and record the time it takes for just 10 revolutions, or 10 orbits of the ball. So starting start. And that's 1, 2, 3, 4, 5, and actually, sorry, it's just 5 revolutions. Yes, just the time for 5 revolutions. Okay. Once you've got that information and you've used your phone or mobile device or stopwatch to get the time for 5 revolutions, then you're ready to start filling in the data sheet. So let's just pop over to that. So the data sheet, you could fill it in right away onto a spreadsheet like this, or you can fill in the data sheet down below right here. So let's see, we had speed of 2 meters per second, a radius of 0.25, a mass of 3, and we record the force. And then using my stopwatch, I had 13.57 seconds, which means I got a period of 2.714 seconds, which is pretty close to the simulator, which is 0.785 seconds, it says. Okay, it's in the same ballpark anyway. Then I'm going to just go through this sheet and modify the speed to change the force. It's going to go from 1.2 meters per second all the way up to 2.8, while keeping the radius at 0.25 and the mass at 3. Then what I'm going to do is change the radius so that it goes from 0.05 to 0.15 all the way up to 0.45, while keeping the speed at 2 and the mass at 3. And then finally for part C, I'm going to keep the radius at 0.25, keep the speed at 2, and then change the mass from 1 kilo all the way to 5 kilos. Once I have all this information done, okay, what you could do is you could just highlight the table that you've been filling in, okay, like this. And then you can choose a spreadsheet application program. So what you could do is use Google Sheets. Just paste it into Google Sheets. So everything is in there right now. Let's see. I see the titles kind of got messed up when I did that. That's no problem. You can just retype in the titles so it looks like the following. If you have the titles fixed, then you can also format it just to look a little nicer. So maybe give some bolding for the labels. Okay, then if you feel like it, you can add some lines like this, just to spread out the different parts of the lab. So just using a borderline like this. Okay, and then if there's any major areas where you're doing some calculations, like over here, you can also add a border if you like for that. Also do a border label right here. And there we go. It's a nice, well-formatted spreadsheet. So now you do want to finish copying and pasting all your other values over as well, or you could just fill it all into the spreadsheet to start with instead of filling in the paper copy. And once you're done, it'll look something like the following. So at this point, what I've also done is bolded the values I was changing in each part. So part A, I was changing the speed, which affected the force. So that is bolded. In part B, I was changing the radius. And in part C, I was changing the mass. Now we just need to make 3 graphs, one for each part. So what we want to do is see how the period, which is right here, okay, is affected by changes we make in the with the speed or the force, and then with the radius, and then with the mass. So the first thing I'm going to do is highlight the period. Hold the control button down on my keyboard. Then I'm going to highlight the force values. And I'm hoping that the computer will get this right and create the correct chart for me. It did not. So in that case, you want to change the chart type to a scatter plot. And then you got to make sure it has the right X and Y axes. So the X axis should be the force, which is in column C. So it did get it backwards. There we go. And then the y-axis should be the period, which is in column G. There we go. And we got it. So then we're going to go to Customize. And you can add a chart title, which might be T versus FC for centripetal force. Okay. And then after that, you can click on Series. Scroll down to the Trendline button. Checkbox, sorry. And then instead of a linear, you want to use a power series. There we go. And then you want to see what the equation is, like that. There we go. Perfect. So then this chart belongs to part A, and according to this, we got an exponent of 0.561. So you just need to write a little comment. Part A, we expected an exponent of negative 0.5, and we ended up with negative 0.561. So that's pretty good. That's not too bad. The next graph you want to do is, so let's try doing the radius first. So it's going to be the radius, and then the period. So remember, I'm holding the control button down. If I just try to scroll across like this, I'm going to end up getting too much information. So just highlight your first column of information, hold the control button down, and then highlight the second one. And then from there, I'm going to go insert chart, and I'm going to go to, let's see, the type of chart. Once again, should be a scatter plot. Computer got it wrong again. And then I'm just going to check my X and Y axes. So the X axis should be the radius, which is column D, so that's correct. And my Y axis should be the period, column G, so that is correct. We're all good here. Then I'm going to go to customize. You can add a title to your chart. So this would be T versus R for period versus radius. And then I'm going to go to series again, and I'm going to add a trend line. And this time also should be a power function. Hoping to get a square root function, so we'll see what we get this time. And I get equation 0.953. So that's not too good, but at least it's in the ballpark. It's looking a little bit too much like a linear function, but it really should be a square root function. So we expected a exponent of positive 0.5, and we ended up with, or you can say something else similar to that, 0.953, so positive 0.953. So it's in the ballpark, but that's not too good. So you're going to have to do one more graph, this time with varying the mass. And then once you're done, you want to do a graph with all of your data to see how the period depends on the square root of the mass, square root of the radius, and the divided by the square root of the force. So now, to type that formula in, or any of these formulas, is pretty easy. To calculate your period, all you have to do is go equals, click on the time you had for the 10 cycles, and then go /10. You press enter, and then you can go Control C or copy, and then you can highlight the rest of the column, and you can go edit, paste special, formulas only, and it'll copy the formula all the way down for you so that you don't have to type in the equation 15 times, and you don't have to do it on your calculator. You should never do things on your calculator when a spreadsheet can do it for you. Now this one's also equals, very easy to do, equals SQRT bracket, my mass, which is right here, close bracket, star for times, SQRT bracket, the radius, then slash for division, SQRT for square root of my force. There we go. Press enter, and then you can copy that down. Another way to copy things down is just to grab that little blue square right here. See how my cursor switches into a crosshair or a plus sign? You let go, and it copies the formula all the way down. You can see right here, up here, there's the formula I typed in. If I go down one, it says E3, D3, and C3. If I go down again, E4, D4, C4. This saves me the time and effort of typing in the formula 15 times or doing the calculations on my own with a calculator for about an hour, right? So see how quickly I could get that done. So you're going to make your last graph is going to be the experimental period versus the root M root R, root FC. This time I'll highlight the titles too, and hopefully this will work. I'm going to go insert chart. Oh, look at that. It actually knew it was a scatter plot. And let's see. The experimental period went on the x-axis, and the accepted value went on the y-axis. So that's backwards. That's okay. So we'll fix that by switching it around. So the experimental value should go in the y-axis, which is called the series on this computer. And the x-axis should be root M, root R, root FC. And you can see it kind of lines up. You can see there's a nice linear function here. So then I'm going to go to Customize, and for the chart title, that's fine. I don't have to change that this time. And I'm going to go to Series, and this time you do want a linear trend line. So I have my linear trend line, and I'm going to use the equation, and there we go. And that's going to be my last graph. Now for your last graph, let's see, I got a y-intercept of 0.399 and a slope of 9.22 right here. And if I take a look at the lab sheet, according to the start of the lab, I was expecting a, let's see, I was expecting a slope of 2 pi, which is like 6.28. So that's pretty close. And I was expecting a y-intercept of 0. So hopefully you'll do the lab more carefully than I did, and you will get better results. Now, if you'd rather do your spreadsheet work in Microsoft Excel, it's pretty easy to do. So I will copy the data over there. Just give me a second here. So it's going to grab all this data. Okay, Control C, grab it over to Microsoft Excel. There we go. Come on, computer. Paste, special, oops, there we go. Paste, values only. There we go. And then you can also make it look better, of course. Okay, and you can also do the same formula work in Excel that you can do in Microsoft, certainly in Google Sheets. That's no problem. Making the graphs is a little easier in Excel. So for example, I'll highlight the period for the first 5, hit the control button and grab my force values like that. And then when I do insert chart, looks like this one here. Let's see, does this one make sense? Check that out. The y-axis goes from 0 to 3, which is kind of like the values for the period, which is correct. And the x-axis goes from 0 to 80, which is correct for the force. So it even got everything right. So that's great. So that's T versus F, C. And then what I'm going to do is go to the chart, and I'm going to right-click on one of the lines, add a trend line, and that's where it's going to be a power function. And I'm going to ask it to display the equation on the chart. And there's the equation. And if I want, I can even, make the equation easier to read, like size 16 or something like that. And once again, I was expecting an exponent of negative 0.5, and I got negative 0.317. But I find Excel is a little easier to use, but it's very similar to Google Sheets, which is free. So it's up to you. Okay. And so once you're done, then in the lab report, once you've got your graphs done and your spreadsheet done, and you've got all your information collected, the next thing you have to do is just answer a few synthesis questions. So draw a free body diagram and explain why it's impossible for the rubber stoppers to revolve flat or 0 degrees or perpendicular to the tube. Then answer question 2 about what happens when the frequency increases. And then question 3, give an example of each of Newton's 3 laws in the lab. First law, second law, and third law. And then based on the percentage errors, the 4 percentage errors from your 4 plots, did you or did you not prove that centripetal motion works? And is our derivation of the formula right here correct? Okay, if you get small percentage errors, then you have proven centripetal motion is working. And that's it. You don't have to do anything else for this lab report. Okay, thank you.